Okay, YouTube, in this video we're going to be exploring further how to solve trigonometric equations, but specifically those that have, say, different types of trig functions in them and that make it a little bit more difficult to isolate what it is that we're looking for here. So for example, like on number 5 here, we have tangent of x plus secant of x is equal to 0. This would be a situation where, getting tangent by itself, it's really in, terms of secant and secant's in terms of tangent. It's not very helpful when you use inverse trig functions on things that aren't inverses. And so basically, our tact is going to be to, as much as possible, just try anything. And in this case, it's going to be to rewrite these equations in terms of sines and cosines or use identities, okay? So we'd say that these equations can often be rewritten in terms of sines and cosines and manipulated to make easier to solve. It's not always true, but this is sometimes, many times, I guess, true. So looking at this equation right here, basically what we're going to do is we're going to rewrite, say, tangent in terms of sines and cosines. That'd be sine x over cosine x plus our secant here, and that in terms of cosines would be 1 over the cosine of x. This would be equal to 0. And looking at this, this presents a specific mathematical or algebraic situation where we could absolutely eliminate the denominators altogether. So one method that we use when working with equations containing a lot of fractions anyways is to multiply everything here by the least common denominator. And that's the same tactic that we're going to take here. And this is something that we can do because there is no way that this cosine of x in the denominator in either of these fractions is going to cause this overall value to be 0. So we can actually lose the cosine of x completely. So our method is going to be this. We're going to rewrite in terms of sines and cosines and then multiply by the least common denominator. So we'd say rewrite in terms of sines and cosines. And then we're going to multiply both sides by the least common denominator. And so in this particular case, you can see that, between, say, sine over cosine and 1 over cosine and 0 over 1, our least common denominator is going to be cosine. So what ends up happening is we're going to go ahead and multiply both sides here by the cosine of x. And so I suppose we could throw this cosine x over 1 here. We essentially just get distribution on the left, and on the right we're going to get multiplication by 0. So 0 on the right, and on the left side here, the nice thing about multiplying by the LCD is remember that it has to share factors with these denominators because it is the least common denominator by the definition of the fact that it contains factors from everybody's denominator. So we would say multiplying here, we'd see that our cosines would cancel out, and we get left with sine of x after we distribute through our first term here. So we have the sine of x, and then multiplying cosine x over 1 times 1 over cosine x. Those are reciprocal, so we just get 1. So you can see that knocking out that denominator now is put us into a situation where suppose we could subtract the 1 to the right side here. We could say taking the sine inverse of both sides, we get just x on the left, but sine inverse of negative 1 on the right side. And so we're asking this question, what angle is it that we take the sine of and get negative 1? Well, of course, in the unit circle, sine is only ever equal to negative 1 down here at 3 pi halves. So we're going to say x is equal to 3 pi halves plus the period length of sine in terms of multiples of that. And that's our only set of answers there. Now, number 6, just another example here. I'm going to try the same tact, but what I want to start by noticing is that we have something here that's not even set equal to 0, and second of all is in terms of more than one type of trig function that is, not sharing any common factors, and so not factorable, we can't isolate it. So we're going to try rewriting this. And so first things first, let's do what our responsibilities dictate that we do, which is move everything over to this left side here a lot of the time and set it equal to 0. So looking at this here, I'm going to go ahead and rewrite our cosecant. We have sine x plus 2 times 1 over the sine of x minus 3 equals 0. And just to be clear on this, I'll even rewrite this here. We get sine x over 1 plus 2 over 1 times 1 over sine x is really 2 over the sine of x. And then we say minus 3 over 1 equals 0. The fact that we have this sign down here means that if we were to now multiply both sides by the least common denominator, which in this case is the sine of x over 1, sine x over 1. Again, on the right side we get 0, but on the left side, distributing this through, let's go ahead and list out what we get. Sine times sine is going to give us a sine squared of x here. Plus now if we take sine over 1 times 2 over sine, the sines are going to cancel out here. We're just going to get left with 2 as the value of our middle term. And lastly, take this sine times a negative 3, we get negative 3 sine of x. So I am going to do a little rearranging here. We often like to have our exponents in decreasing order. But I hope what you see here is that this is a factorable thing, or at least we should check to see that it does factor. It seems that it will. So in this case, we'd say, well, putting signs of x in the front, it's nice to have an a value of 1 every once in a while. We'd say this would have to be a sine x and a sine x, and because a is 1, we can go ahead and ask it this way. We'd say, what are two factors of a positive 2 that have to be a negative 3? And so by my count, it's got to be a negative 2 times a negative 1 gives me a positive 2, but adds up to be a negative 3. So if these are our two factors here, here's what we're going to do. Because we have two factors multiplying out to be 0, we're going to set each individual factor itself equal to 0, of course, as we do. And so we would get sine x minus 2 is 0. In this case, we get sine x is 2. And so if we take the sine inverse of both sides here, we get x, the angle is really the sine inverse of 2. In other words, we're saying what angle did you take the sine of and get 2? And anybody who knows their unit circle knows the radius is 1. And so that it is impossible for sine to ever be anything that is outside of negative 1 to 1 range, okay? So we'd say that this has no solution because sine, the y values on the unit circle, never equal 2. So we'd say no solutions, at least for this part of the equation here. So looking at our other part of this equation, I'll go ahead and switch colors here. We say sine x minus 1 is 0. This would only mean that the sine of x is equal to a positive 1, or that when we take the sine inverse of both sides, we get that the angle is the angle that we get when we take the sine of it and we get 1. So again, where is sine equal to 1? Given that sine is y values, we would say that sine is only ever equal to 1 right here at this angle. And so we'd say that this angle must be pi halves, or 90 degrees, plus multiples of the period of sine, which is 2 pi. Cheers.